Wonderful. Now we can move on to the latter part, resistors in series and parallel and their simplification. So let's see how we simplify resistors in series. Let's define a simple circuit with Vs, Is, then we have R1, R2, R3, and R4. Of course, we can define the respective voltages as well, V3, V4. We do not always denote the voltages and currents for each. We assume that we know them. Otherwise, the drawings can get rather cluttered. So we can see that Vs using KVL is equal to V1 plus V2 plus V3 plus V4. Wonderful. Noting that the current in any loop is the same, so we can substitute this as usual. Ohm's law comes into play again, R equals V of I. So we substitute V equals Ri, so we have R1 plus Is, or multiplied by Rs, plus R2 times Is plus R3 times Is plus R4 times Is. And we can simplify Is out, Vs out, group these two, R1 plus R2 plus R3 plus R4. Perfect. Then we can get R equivalent, which is Vs Is, as the sum of R1, R2, R3, and R4. So we can see that resistors in series simply sum. So this is R equivalent. So that resistance is the equivalent value of all of those resistors added in series. Wonderful. Let's move on to resistors in parallel. We define the circuit. Now all the resistors are denoted as being in parallel. So we define Vs and Is the same. See now all these resistors share a common top node and a bottom node. So this is resistors in parallel and this is resistors in series. Now all of these currents are no longer the same. And I3, so that's I1, I2, and I3. Noting that the voltages over this node is the same. So the voltage over a common node is always the same, and the current in any loop is always the same. Or at least a closed loop such as this one, and a node such as that one. So we can use KCL this time. Say Is is equal to I1 plus I2 plus I3. Perfect. Then again, R equals V of I, Ohm's law, the real fundamental equation in any of circuit theory. Is equals V1 over R1 plus V2 over R2 plus V3 over R3. Except now we know that V1, V2, and V3 are all equal to Vs. So again, Is equals Vs over 1 over R1 plus 1 over R2 plus 1 over R3. We have to be careful with the algebra here. These, because they're in the denominator, we cannot simply sum them out, so it has to remain within this form. So R equivalent, or essentially 1 over R equivalent, is Is over Vs, which is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Perfect. So usually we can denote R equivalent as, let me grab my ruler, 1 over R1 plus 1 over R2 plus 1 over R3. Just like that. So 1 over R1, R2, R3. And that is R equivalent. So this, in the simplified circuit form, would look exactly as that, with Is still flowing there, and Vs still being over that node. Perfect. Then we have a special case of resistors in parallel. We have the two parallel special case. So let's ignore R3 for the time being. We have R1, R2, Vs. Alright, so we know from this equation 1 over R equivalent, from this part of the equation 1 over R equivalent is equal to 1 over R1 plus 1 over R2. Now, we can, if we would like to, simplify this as R2 over R1, R2. So essentially here we're finding just a common denominator between these two, and then we sum that. So then we can define R equivalent as R1, R2 over R1 plus R2. So essentially we just summed over there because they have some denominator, we can sum over them, so it's R1 plus R2, but this is 1 over R equivalent, so we flip this whole equation, so it's R1 times R2 plus R1 over R2. And that is just a simple quick hand if you ever have two resistors in parallel. Let's do a simple example that highlights the simplifications of resistors in series and parallel. So we have a voltage source, a resistor here, there, there. So we have a 10 ohm resistor, a 2, and we have a voltage source, Vs, and a current Is. Noting that I'm not even adding the unit at the end. This should always be done, but unfortunately we're not all that inclined. So let's first observe some things. This resistor is in series with these two resistors. However, these two resistors are in parallel with one another, so they share nodes, this top node and this bottom node. So let's first simplify the parallel combination of those two. And just as we've defined earlier, because we have two in parallel, we can use this equation over here. So R parallel is equal to R1 times R2 over R1 plus R2. So we have 2 times 2 over 2 plus 2, which is equal to 1 ohm. Wonderful. And then we can simplify these two because they're in series with one another. We just add them. So the circuit simplifies to this, which is R equivalent, is simply the sum of 1 plus 10 is 11 ohms. Wonderful. And that is all for today. So what we've done today is Kirchhoff's current law, Kirchhoff's voltage law. So the sum of all currents in any node is equal to 0, so that all the currents flowing in is equal to the currents flowing out. Kirchhoff's voltage law is the sum around any closed loop of the voltages is equal to 0, so all of the voltages in a loop is equal to 0, so this voltage source is equal to the sum of V1 plus V2. Then we did a simple example utilizing KVL and KCL. Then we did a simple example using a dependent voltage source, which was defined as Vs equals 3Is. We defined how resistors simplify in series and how they simplify in parallel, and we did a simple example utilizing both of those concepts. Noting that R equivalent in terms of parallel and series, this can be expanded. If you have more resistors added into the circuit, you can simply add over here. So R equivalent can be essentially R1 through Rn, as well as R equivalent here. This can be 1 over R1, 1 over R2, 1 over R3, all the way up to 1 over Rn. Perfect.